1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, let's finally continue discussion of Rossnagel's paper. Yesterday I was reading for 5 hours this paper, and I thought to do stream yesterday, but I didn't do it because it takes really so much time, and I want to confess that without streams I would never be such focused and be able to dive such deep to the statements, because that's like the limit of how you can think much about the article. After 5 hours of thinking on your own, you feel exhausted. You most likely will feel exhausted. And I'm not Superman, of course. I also feel tired. I feel bored. I feel that I'm lost in information. And this great application, of course, helps me. But still, if you sit a lot on your own, then it takes a lot of energy and you feel really exhausted because of just sitting alone. And right now there is no one who wants to discuss for 10 hours this article with me. And also discussion with someone will be even longer than discussion with viewers in the future. So it's very hard to find the person who wants to really think about all the statements, which are very unclear, as you can see from the previous streams. That's why the only way how to be productive, the best way how to be productive, is to do streams. And maybe later it will help someone to read this article, because he or she will not need to think about unclear statements again, and I will think instead of them, and then they can continue from this not zero level of thinking about the article, which is already like saving 20 hours at least for only this article if it's really needed. But right now it's very unlikely, of course, that someone will need this article and will like to watch streams. But okay, that's just the preface. So I really hope that today we'll do the 4th part out of 5, and tomorrow or today in the evening there will be a stream about the last stream. I hope the last stream about the 5th part, about the discussion of Chernysty wave and peerless transition. So that's the place where we have stopped during last stream, and that's the structure of the stream, of the article, I mean. So the plan for today is to do only these 2 big subsections: review of ARPES results and empirical tight binding model. So here it will be said that, hey, there is ARPES, it gives different results, and here are a lot of comments about them. And here it will be said that we're using some models which can be found in the cited papers, and we feed, I guess, parameters, and they somehow match. So later I was even reading a statement that Rossnagel says that, again, the model that is introduced here in the first section, parallel instability, is still applicable, but I don't know why, because before, as far as I remember, he was saying that it's a bad model, it's a weak coupling model, we need a strong coupling model. But later he will say that actually maybe that's the best model which we can work with. So that's what I remember after the preparation yesterday. And I really hope that the stream will not be more than 2.5 hours. And maybe I will gain some skills and be doing it faster. But okay, let's just start thinking about the theory, and that's the plan for today, just to these sections which will spread for approximately 2 hours. I don't think that the stream will be less than 2 hours. But right now, of course, if you have clicked on this video, you already know how long is the stream. Let's just open the summary of the article, and as you can see, I have added key formulas, and basically that's all. Maybe also added this plot, which will be today discussed. And okay, tables might be also useful, but yeah, right now they're not that useful. And I need to delete this description, of course. Okay, write myself. Okay, let's use this beautiful note. Yes, questions from the stream. Of course, we'll remember that we need to delete this because that takes our attention and we don't need it. We have a theoretical part for it, but I don't want to keep anything in mind, so I just wrote it for my future. Okay, so let's continue reading, and reminder, I have already read it, but that's the announcement of today's discussion, that we will discuss ARPES results, and maybe it will give us some ideas about charge density wave mechanism. Of course, it's not clear what do we mean by clues to possible charge density wave mechanism, but Rossnagel writes it in all the paper on approximately every page, that we need to understand the mechanism. Okay, now let's start reading finally. Okay, here it's written that ARPES is a well-known method and well-used method. I don't know what was studied in all of these papers, because it would take at least a week scrolling through papers to answer the question what happens exactly in this group of papers, that group of papers, except that of course they're related to these materials. But something there happens, and I guess key parts of this experimental works are summarized here in the article, so that's what we're going to see very soon. Okay, this sentence is not one that I added my comment, which is maybe because I forgot to do it or to read. But here it's written that for some reason we are focusing only on single particles energies and redistribution of spectral weight. So I understand it as the synonym of bands, an introduction to bands. So here there are bands, and they correspond to single particle excitations, I guess. And each band has a spectral weight. I still have in my to-do list a task to understand how exactly we can have different spectral weight on a band. Maybe there are several bands in some little region, but okay, that's what happens in scope of this theory, and maybe like basic preparation is enough to understand it. So here it's written that we will focus on such plots of single particle energies. But I don't know how it can be non-single particle energies. I just forgot to add the comment here. I will add it later. Yeah, and basically that's the same thing here, that if we focus on single particle energies, that many body effects will not be considered. What does it mean and what are we missing because of it? It's very unclear, because later he will say that, hey, in the experiments that we have, this is the experiments, we have this marrying, so maybe it originates from any body effects, because anyway electron interacts with a lot of other particles there. So it's very likely that it's from any body effects, but for some reason Rossnagel decides not to discuss it. I don't think, I'm not sure that it's a good idea, but okay, let's just follow what he has presented to us. Okay, here, that's the figure 6. Let's just check. Yeah, that's the figure 6. And that's the introduction to this figure. So ARPES, yeah, I haven't prepared introduction to ARPES because I still haven't read this book. However, as far as I understand, I have already copied it, maybe 8 or 9 months ago, but then I wasn't opening this book, so I can't comment much what ARPES is. But based on this text, I understand that that's a special device where we shine some maybe electrons on the material, or like photo emission spectroscopy. So maybe we shine photons and then they emit light, and then somehow it's detected, and we get, as far as I understand, 3 types of plots. I mean, okay, maybe 2 types of plots. The one is the Brillouin zone and the energy levels in the Brillouin zone. Another one is the spectra, again in the Brillouin zone. So I wasn't working with experimental part of this field much, so we know these directions in the Brillouin zone. These are these directions. They're shown here. Unfortunately, I can't explain right now why we have exactly this plane. It's Km gamma. So here, gamma Km. So yeah, like I don't know why exactly this is the plane. And I don't know how can we measure it by photo emission, maybe because of the title of ARPES. But it's not the thing that I wanted to discuss, because anyway, in scope of this article, we're given these results, and we will discuss its features and its meaning, and that will be for approximately an hour. And then the binding model will be also for an hour, and that's how I imagine today's discussion. Okay. Okay, now, okay, let's check here, first of all. Yeah, so here we should understand that that's for normal phase, that's for commensurate phase. So we lower temperature, there is this appearance of charge density wave for bulbs of electronic distribution, which are discussed throughout this paper. And and that's the state where they are present. That's the state where they're not present. Right now I'm thinking about this temperature, and I forgot that is it the temperature above? I mean, it should be above the transition temperature, but later, so I think later it was written explicitly what is the transition temperature from normal state to like incommensurate state, so it should be a normal state. And then after incommensurate state or something, we will have the commensurate state, and that's for commensurate state. It's interesting also how does this plot look like for other states? Let's write it to the list of questions. Yeah. Okay, well, that's not what is discussed here, so that's just a question for future thinking. And here we have just changed from the normal state to a commensurate density wave state. All the features will be discussed later. Here we are also given information about like experimental setup. So that's the laboratory, like where the laboratory is located, energy resolution, yeah, but by energy resolution I don't know what it means. So maybe we actually have here squares somewhere, and it's a pixeled plot. But we don't see squares because they are like we are far from them. The resolution is approximately big. Maybe that's what is meant by the resolution. And yeah, if you want, you can. I mean, I don't think that something is really useful here. Okay, for the reference, we know where this experiment was done. Okay. Well, so I was always thinking that the next figure 7, which is this one, it was obtained from theory, but here it's written that the abstract schematic view of electronic structure, this figure. So maybe I should consider this figure as the one that's obtained from experiments. And interesting that here we see only here some signature of a band, but here we are written and there are these bands. And I don't know if we can think like this, because if we don't see a band, maybe there is no band, and if there is a little density of states on these sides, then doesn't mean that we have a band. We don't see anything. Oh, okay. That's another good question. Yeah, of course I don't know the question. Here we are told that the figure 7 is abstraction of the figure 6. So I guess that was obtained from experiments, and then there will be a fitting of this image. Okay. Okay, I'm distracted a little bit on one message. Let's read finally what happens here in this figure. So that's what I have already explained, that these are the bands, and the spectral weight is bigger only on this regions where we have a gray areas. And I have already written a question that why do we have a gray area here if we don't have a band here? So that's the thing that I consider unexplained, like the one that is not explained is the one that is not explained. And that's what's shown here, that for some reason that's what happens, that the spectral weight is different and it's higher here, and it will be said in the future that it will be these regions correspond to this undistorted band. And here, okay, maybe okay, so here it's not written explicitly because here it's written that a lot of research were made and results are illustrated. So I was thinking that this is a collection of other results, but here it's written that our results. So it means that the previous figure was from Rossnagel's results or his colleagues. I don't know. And here it's written that it's also in a good agreement with other results. So I need to look at these papers to see other results. It's interesting actually to compare what is done here with other papers. It would be way easier to read other papers because, like, in general, a lot of concepts already are familiar after reading, for me, after reading this paper. So maybe later one day I will check other literature and say and tell you how these results are consistent with these results. Okay, but here we're told that they're consistent. Next sentence is very unclear. There are some discrepancies, and so which discrepancies is also not explained, but the reason for them is also not clear. There are some matrix element effects and experimental geometries and photon energies. Like, we know what is photon energy, know what is experimental geometry, but it's very unclear how it can give a different result of the ARPES. And what is the matrix element effect is not the thing that I know at all. Yeah, it's also not clear why there are plots of different types. So it would be nice to compare them of the same type. But here there's plot of one type, there's plot of another type, and that's plot of also another type. It looks like a mixed plot because here we have Brilliant zone, here we have just Brilliant zone energy, and here we have no energy, and again the Brilliant zone. But I don't have much experience in the experimental side of this work. So if I don't know if this region, horizontal region, is the same as this horizontal region. Here we have ky, so maybe we go along the y-axis, but that's a bad part of the article because we can't compare them. The plots are of different type. And what can we say about it? I don't know. I also don't understand the statement, why do we have a shrinking of a Brilliant zone? Because as far as I understand, somewhere there in the article, maybe in the future, when we will be discussing tight binding models, it will be assumed that that's the initial Brilliant zone, this pentagon 1, 2, 3, 5, 6, 7, 1, 2, 4, 5, 6, 6. So hexagon. But then after charge density wave, we have the shrinking to this size. But as we see, like there are different areas in this initial brilliant zone, so that's also a little hexagon which has a different structure comparing to this one or to this one, and all of them have different structures, even though they're rotated, but still. So I don't know why we have a shrinking of a brilliant zone. Let's actually write this as a question. Okay. Maybe I'll find later, but most likely only through theoretical papers, not in this paper, definitely. What does it mean? Why there was such? I don't know why did I write this question, because yes, as usual, that's before shrinking, that's after shrinking. I mean, before charge density wave state, and that's after charge density wave state. I also don't understand why we are told that that's just a typo here, that there are some dotted lines. Of course, we don't see any dotted lines, but I thought that what is dotted is this little hexagon. 1, 2, 3, 4, 6. Yeah. But we don't see any dotted lines. But what I'm not sure about is that we have 3 times 3 Brillouin zone. I thought that that's the big one, 3 times 3 Brillouin zone. But here it's written that 3 times 3 corresponds to dotted lines, and as we can see from this plot of the figure 7, the dotted lines, okay, slightly dotted lines are 1 times 1 hexagon. So maybe Rossnagel just confused notation 2 times. First of all, he didn't do the dots. Second of all, of the lines. Second of all, he confused what corresponds to what. That's just my understanding about it. And anyway, that's not really important, because there is some theory assumed here by which gives us shrinking of the Brillouin zone. It's not explained, so we don't know why it happens. And if we learn the theory, it will be obvious what is meant here. Nothing is meant which is not shown in this picture. Okay. And then again, that's the reason why I was confused. That figure 7a, is it experimental or theoretical work? And here it's written that already that's results of tight binding calculations. So that's the place where article contradicts itself. So first it was written that it's from experimental results, now it's written from theoretical results. Maybe that's just a great fit and both statements are correct, but it's also not written here. And based on tight binding models, people understand this band structure. I was trying to understand how tight binding model is consistent with the electron-phonon interaction model, whereas there is Fröhlich Hamiltonian, and also with parallel instability, which is presented in the beginning of this article. So I don't have a clear answer now, but my version is that like parallel instability can be driven from electron-phonon interactions, and the binding model is approximation for electron-phonon interactions and some clever transformation of it, of the Hamiltonian, Fröhlich general Hamiltonian. So so that's very unclear, and links are not given to us explicitly. But I guess that it's meant by tight binding model that we will like simplify the model that goes into the parallel instability. And if parallel instability was working for initial Fröhlich model, then for tight binding model should also work. That's how I understand the connection of the statements, that we can maybe rederive this instability for tight binding model somehow and show that it's there, or we can solve tight binding models somehow numerically and show that such is this is the change of the bands. But that's all is just a reference to cited papers, and we need to read theoretical cited papers in order to figure out these connections. But during this stream, we are just focused on tight binding models, and we can maybe even forget everything what was written before. There are just these tight binding models, there are these experimental results, and maybe theoretical results are also exactly like experimental results, maybe because of the fitting, but we will read the statements a little bit later when we will go to the section about tight binding models. Okay, that's what's written here. So here and later it will be written a lot of times that 5D band, other bands, and I have no idea why is it D or other bands. I have some like intuitive approximately understanding that D band is closer to the core of the atom, so electrons can easier hop, or maybe not close, but vice versa. But I have left all these questions of the type of bands. Later we will see a lot of such names of the bands. And I don't have a clear explanation for this case and for other cases, so I will maybe later not comment. We are just told that it's exactly 5 band. It's a really big question, which may be a good idea to try to answer using AI, but I haven't reached this point. But okay, that's description of the of this side of the plot. Maybe from this direction to this, from center to the maybe that's the illustration of this Brillouin zone. So from center to the side and to another side, M and K, from M and K. But I also don't, okay, maybe that's because of perspective. This gamma M looks less than MK, and here gamma M looks twice bigger than MK. That's what happens, maybe. That's just description of this plot. And here it's written the connection between some plot of Fermi-surface of the Brillouin zones, but that's not this plot, because on this plot we have a different material, so we need a plot for tantalum disulfide, and it's not here in the article. Okay, we are advised to scroll to figure 11. Okay, let's scroll to figure 11. 13, 12, 11. Okay, that's the plot for figure 11. So I'm really confused of everything here because I was trying to interpret what's written like this a feed from theory, but here there is this plot which is explicitly telling us that that's the feed from theory with all of this spectral, big spectral weight here and little spectral weight here. So that's how the article written, so don't blame me, please. I was honestly thinking about each sentence, and if it's written in a confused way, then I can just tell you this and don't pretend that I understand it. So the figure 11 indeed tells us more about tantalum disulfide, and that figure is also about tantalum disulfide. So maybe we are dealing with purely here charge density wave, and these are our theoretical calculations, these are experimental measurements. Okay, that makes sense, I think. And that's the energy surfaces and Fermi surfaces in the Brillouin zone. So that's the Brillouin zone, that's without the charge density wave, that's with charge density wave. So where is the Fermi surface here, you can ask, and I don't know why the Fermi surface is so fractal. And how does the new state influence it? It's like, just imagine this, like, okay, we have this free electron model, but right now electrons are modulated. And what happens, like, we don't have already a Fermi surface, we have some strange islands. So it's not clear if we should consider these little islands as a Fermi surface or no. It's like fractal Fermi surface, something like this. I don't know. Okay, but we are not going to discuss this section, this stream. That's what I planned for the next stream, because even discussion of this will take us really, really long time. Let's just remember where have we been. I think we have been here, and we are here. So you have seen that elliptical Fermi surfaces, but also it's not clear that here we don't have, I mean, there should be a crossing, but we don't see a crossing. We don't see anything. Why? Okay, it's actually a good question. Why? Let me write it here. That's the good question. Why we have here bands and the experimental plots? We don't see bands here, but we have a link here between these crossings of bands of Fermi surface and that ellipsis which you have just seen. And the link is unfortunately missing, so I can't explain you how this crossing is connected to the elliptical Fermi surfaces. I literally have no idea. I'm not that strong in this theory, and of course I need to like discuss at least 10 papers to be assured in statements here. Then dramatic rearrangement is predicted to occur. Well, that's what we know. I didn't write here this comment, but of course that's what we have discussed throughout this article, that the phase is changed. But here we will see everything is about this plot. So again, we have this 5D bond, and it splits right now into really a lot of different sub bands, or it's written, as it's written here, submanifolds. So instead of one band, we are going to have a lot of bands. And there are a lot of energy gaps between all of them. What is meant by Fermi-surface becomes messy. It means that electrons will sit on this minima of conduction band. And maybe that's explanation of that picture of the Fermi surface. So maybe that picture, okay, maybe that's the answer on the previous question, which I said that how Fermi surface can be a fractal. It's actually not a fractal, but there are some occupied and non-occupied states. I mean, only occupied states are on some minimas, which then forms such, looks like a fractal picture. But that makes me think about, in general, this Fermi surface concept, that it's very hard right now to trace where it originates from, like the whole idea of Fermi surface and bands. Is it obvious? Like, why bands do not depend on the number of particles? If we increase number of particles, we discuss that they feel just states, but the states itself do not change. Okay, I mean that if we have different bands, why wouldn't we have a different Fermi surface at different position? Okay, let's write it here. I'll try to understand this later. Maybe it will be obvious for all people who work with semiconductors, but I'm not expert in this field, so that's the question that I can think later on my own. Let's just assume that Fermi surface is the same as it always there, and yeah, electrons just sit somewhere on this band. And that's what is written here. So unfortunately, that's, as I was saying before, that's the weak part of the article, that we don't see exactly comparison of theory of what is calculated and experiments which is done. Maybe, as I was trying to guess, that was the experiment and figure 11 here was the theory, but I just need to guess because figure 11 will be in the future, and right now we have only figure 6 and 7, and here maybe that's the picture that they assume, and that's the ARPES measurement. but in general, that's not important sentence. You can, and you should maybe forget this sentence. Because here it's written that figure 7 is obtained from abstracting ARPES results, and of course it's consistent because you have obtained this picture from experiments. And that's how you can see it. And why do we need to read that it's consistent? It's very unclear. Okay, now we have some advanced comments that there is this fine structure of this subband. I have no idea what it means, but that's advanced property of these bands. And also, okay, existence of them was confirmed somehow, which is very strange because here we, in the figure 6 here, we see explicitly that no, there are no such bands. There is just this one band and some distortion of spectral weight, but we don't really want to draw anything else. Maybe here there is a band, but most likely no. Maybe this band picture is at all not applicable in some of the regions. But somewhere there, some people did some other experiments and came to some other measurements, and maybe this is not the precise measurement, and we need a different measurement, and they did a better measurement, so they noticed these subbands. That's how you can understand it, maybe. And also, that makes us, that brings us to the very important question that before, in the Perles model and all of discussion of it, there was nothing about subbands except the discussion of excitonic insulator, where it was subbands were presented as purely different model. So it wasn't a tight binding model, it wasn't of like electronic structure, it wasn't electron-phonon interaction, it was a purely another model where there are electrons and holes. And was there some special formula? Let's just check. It's very easy with my app. I just click the table of contents and then click PDF, and now I'm given the PDF and I don't need to scroll finally. So this model looks like a very different model. We have the delta here, we have hopping in between bands. We don't have electron-phonon interaction, we have just interband interaction. And I don't feel that Rossnagel really understands this excitonic insulator model, because theories here is just a collection of formulas that looks like he wasn't using them. But okay. Let's continue reading. That's the weak part of this theory, that we are given that we have different bands, but in all models before we don't have any bands. Okay, that's how it's written here. Anyway, we need to read cited papers to understand theory behind it. And okay, maybe these gray areas mean the subbine dispersions or something else, but that's like as was written before, just a bigger spectral weight. So it was confirmed, all of this was confirmed by experiment. That was what we are promised here in these sentences. But now the question is that if we have this in the experiment, what will it tell us about the Chernetsky wave effects? And there are several versions of it that was written here. Okay. So nothing is written about the temperature, I mean, the phase diagram, and the thought that undistorted phase starts above 380 something Kelvin. Here it will be written somewhere. That's why I was thinking a little bit more about it in the beginning of today's discussion, but where was it? But I definitely was reading it. I just confused. I'm confused. Wait a second. I remember vividly that it was written that we are working at 390 Kelvin or something. Let me maybe try to understand it. If I don't understand it, then I'll just go further. Okay, let's check like this. Okay, there's no way to find it, and I don't have, unfortunately, right now an assistant to help me find this information. But like, really, why do we? Okay, I have literally no idea where was it written, but I remember that I was today discussing that the aha, that's where it's written, 390 Kelvin. And you see, like even if I did a search on the text, I would not get it because that's written in the image. So here we are told that that's the normal phase, and I thought that that's undistorted phase. Right, but here it's written. Where is it written? Where wasn't? Okay, yeah, here it's written that it's 543 Kelvin, and that's what I'm confused because before it was written like 390 Kelvin. Now it's written 540 Kelvin. Okay, well, let's write it in questions. Yes, that's the contradiction. Before we were told that it's 390 Kelvin, then we are told that it's 443 Kelvin. How to understand it, I have no idea. We need to read cited papers. I mean, it's written that we don't have ARPES results for this undistorted phase, but before it was written that above 390 Kelvin there is undistorted phase. That's the question which I was thinking about. Oof, okay. Basically, it's written here that we can extract that undistorted phase from that phase at room temperature. But it's not at room temperature because room temperature is 273, okay, 290 Kelvin, and we have data at 390 Kelvin. So it's not definitely room temperature results. But anyway, that's a little thing, the minor thing. The thing is that somehow we can extract undistorted phase spectral weight, right? Because of superlattice crystal potential small, and that's what not clear at all, why we can extract that dispersion of this dispersion if lattice potential is small. But if lattice potential is not small, why wouldn't be able to extract it? I don't know. And here we have a comment about what I had told you, that like it's not clear why for me. I don't know how it works, but the statement is that the spectral weight is bigger only these gray areas, and these gray areas are similar to this region. That's reflected region, so that's the line. No, that's the line. I was also confused. That's the line of the band before, and that's the line of the band after, and here it's along this line. Why? I don't know, but that's what's written here, and that's what maybe is seen from experiments. But also maybe it will be from the measurements. I don't know. I mean, from calculations, not from experiments, so not only from experiments, but also from calculations. Okay, nothing is clear what is meant here, but it's written that basically we can use Mott Hubbard model, and I don't know what is a Mott Hubbard model. I mean, maybe it's a typical Hubbard model where we have on-site interaction, but I can't comment much about it because I wasn't in depth studying it. But if we have this metal-insulator transition, maybe because of the number of particles, electrons. So if there is this criteria of phase transition based on number of particles, concentration of particles in the metal. So there are some Hubbard subbands in scope of this model, and thick gray lines. So this model, as far as I understand, can explain these spectral distributions. And right now I really want to have a little break to get some water, so see you in just a minute. Okay, let's continue. Luckily, I have water right now, so I will be able to be more active. So that's how I understand this sentence. Because you see, like, the idea can be not clear, but if it's written in a clear way, then I can't tell you more. What is accompanied by? We can only guess, but I interpret it as it can be explained by, and some Hubble subbands appear, and I guess some of these subbands are Hubble bands. Anyway, we need to look at this model, and maybe this model is explaining something here. Maybe it's equivalent to the straight binary model that will be explained at the next part of the stream. Okay, let's read further. Okay, how does Mort-Hubbard model is connected to strong electron-phonon coupling and electronic correlations? That's what I have no idea about, but that's what is written here. Initially, I thought that we start with the electron-phonon coupling model. By the way, I had yesterday a discussion about what is the parameter of electron-phonon coupling, and I think we didn't came to some conclusions. It could be lambda, it could be G, it could be actually other constants from books about polarons, but here we don't have them, so we have just two parameters, lambda and G, and also that effective electron-phonon coupling parameter. Sorry. Which you remember, like, it was written somewhere where there was a table discussed, and we were told that we can extract this special dimensionless coupling parameter. It was, as far as I remember, gap divided by maximum displacement. So we have these three parameters, and like, that's the disadvantage of this article, because some sentences is better to just forget than to try to understand them. Like, we don't know anything about this model, okay, unless we have education, this condensed matter topic. And this model is presented to be the most fundamental model, and it leads to these two features, the strong coupling. So maybe we can derive Fröhlich model from Mott-Hubbard model, but that's also not the microscopic first principle model. I mean, not the first principle model, it's effective model. And how electronic relations are involved, that we can just guess. Of course, there was some discussion of coherence length, but I actually forgot it, and let's try to restore it somewhere. I don't know, really, nothing was explained about the coherence length, so the only thing I can tell you about it is that it was mentioned. I don't even remember in which paper, actually. Was it in this paper or another paper? Okay, let's not think about it. What happens with electronic relations is, I think, yes, it was here in this paper. I can also find this place. No. So we need to come somewhere here. This definitely in this paper it was written. When we were discussing the stability, there was this argument. Sorry for this delay of the app. Yeah, so for example, here, if we were discussing weak and strong coupling, suddenly there was a coherence length, and it was related to something inherent in these models, but it's not written what, it's just the feature of weak or strong coupling. Yeah. Okay. What I was discussing, let's try to remember. Yeah, so that strange thing is related to this strange thing, and we don't know what is the real origin of some effects, but these are the statement that were given. So that's why I propose to even forget this statement, because nothing is really clear. So, I mean, how can you imagine a less clear statement that first of all we have strong electron-phonon coupling, second of all we have electronic correlations, third of all we have several bands, and that's why we have the different ARPES shape. And that's the very bad explanation of connections between effects that are assumed behind just one measurement. Okay, now we are told about the plot, which I will open you very soon. This one, and in this plot, Fermi-surfaces are not sharp, and they show high intensity features centered on gamma. What is centered on gamma? I mean that the center of all of this picture of all Fermi surfaces in gamma. I assume that it doesn't mean that we have high intensity exactly in the gamma point, because because we don't see it here, right? So that's the only way how we can interpret it, by just saying that that's just description of what we have already seen on the figure 6b. So now you actually see why not so many people are doing science, because all the time is going to just understanding what the author means, and like it's not a productive time. I'm not learning much. I'm learning just statements without any explanation. So that's how my app can actually help, because if I had AI chat and if I had like all cited papers, I could much easier work with the information. But right now it's not the case. So okay, I'm still more productive, but it could be even more productive with the app fully working. Okay, like what is meant by uncertainty in the band diagram Fig A? Maybe it means that this band has uncertainty, so it can be upper, lower. That's what I guess it's meant. And maybe it means that, okay, again, the sentence, that's the sentence that's better to forget. It's not clear what is the relation at all, what relation at all can be for measured spectral wave distribution and measured band diagram. We're given this plot, okay? So why do we need some sentence which asks some abstract question? What is the relation between this position and this amount of blackness? I don't know, but that should all come from some calculation or some model, and don't think that at all we should expect some clear dependence between the position of the line and the okay. And yeah, and the spectral waves. Okay. I just need to go to my app, sorry, and change one thing. Sorry. Okay, let's continue. Sorry for this distraction. Yeah. Okay. Okay. It's very hard actually to do stream when there are some distractions about banking applications, so I'm really sorry for this. Akira said that there are some ideas about the shape of the energy bands and what? Let's check 1 second. Check once. Okay, yeah, and the spectral weight. Okay, let's just go further. The conclusion that is... Yeah, okay, some ideas are there, but nothing is clear here, so we just forget this sentence. Now, the next sentence. Okay, here it's written that we need more precise measurements, and there should be uh, some fine structure effects somewhere there. It's not clear what are the fine structure effects, but we are already told about it not the first time. So, tight binding models maybe not fully applicable. What does it mean? It's not clear. We haven't been working with tight binding models yet. But, and we also told that they are giving good explanations, but here it's written like opposite statement that they might not be applicable. It might be applicable, no, there is no model which is fully applicable because of a lot of effects that go beyond each model, so that's obvious, but again, that's useless sentence and we can't understand it because we need to know what are the spin orbit effects in order to understand the statement. Yeah, okay, so here there's description for the figure 7, which I have already told you. These are the bands, these are the higher spectral weight. The bands change drastically if we go from normal state, homogeneous state to commensurate density wave state. And I have no explanation for all of this. Okay. Okay. Now we are proposed to discuss the second material. The first, the everything before was just about antimony disulfide or this plot. Now we are moving finally to the second material. So so for the second material, it's written that it's easier to fit it to tight binding models because results are better. Fortunately, we can't compare the results because they're presented on different plots of different types. But okay, at least we know that tight binding model is more applicable for this material, for second tantalum diselenite. And yes, we will look at this type of plot where we'll see how Fermi-surface is changed. And yes, it's written here, it's also written here, that look at fig 7b, and Fermi-surface looks like in 7b. How to obtain it, I have no idea, but that's the question for people who are doing experiments. And that's just description, this just comments about what we see already in this CF7b figure. Some circle pockets, I mean, maybe these ones are called hole-like. Why do they call it hole-like? I don't know. Well, that's the only new information. Yeah, well, around which points around gamma and k, around this one and around this one point. These are the hole-like. Why are the hole-like? I don't know, but maybe I will understand it in the future. So now there is this very unclear connection between the band structure along this direction, gamma k, and the band structure. And I don't know why is it connected somehow. We have a cited paper about it. I have no idea about this connection. Parts of so here, if we look at this side of the plot, we can see that there is maybe slightly changes here of the density of states, and that's the precursor of charge density wave. That's what I assume what's written here. I mean here, and below charge density wave we will have a bigger diminishing of the spectral weight. That's what maybe it's written here. Yeah, so we call them pseudo gaps. I don't know why pseudo gaps or not pseudo gaps. I have no idea. So that's the question which will be asked also in the future, that were written that pseudo gaps evolve to real gaps, but I understand what is the pseudo gap and what is the real gap. I don't see here pseudo gap actually, but that's what's written here. That's how we can describe it. And here, these K Fermi pockets are completely destroyed, but I don't agree with the statement that they looks just diminished. So I don't know what is meant by destroyed. This was, as far as I understand, what is meant here. K Fermi pocket, and that was the low, the changed pocket after we moved to commensurate charge density wave. But it's clear about this dog bone, so it was before, now it's after, so it's reconstructed. Anyway, it's I need to change this to green line, but it's clear what's written. We just look at the picture and describe this picture, and we get the right version of this sentence. I don't think that something is meant which we don't see in this image. Yeah, and then we have again description of this image. Now we have a circular pockets. It's also actually, I have noticed only now that here we don't have anything, but here we have this. Okay, let's write it to the question. Okay, I'll try to answer this question later, because we also have these little circles here, but nothing is present here in the experimental study. So what is meant by this little circle? This little circle, I don't really know, but here we have just description of these images. Yeah, and there are these bold gray lines. Should be gray lines. Okay, oh no, gray lines. Yeah, on figure 7b. They also here, and they tell us where there is the normal state. I mean, the spectral weight is bigger. Why, we don't know, but we have a cited paper. And here we are not given some important information and no information at all. So the conclusion is that we need to think. We need to think again about some models behind it. And what we should think about? Let's see. Okay, just energy gapping. So we have different energy gaps at different momenta, and we need to look at these energy gaps again. So it's a useless sentence, but it's about just this energy gaps, this change of the Fermi-surface. Because maybe there is no explanation right now of this change. At least I don't know, of course, and I can't tell you if there is explanation or no explanation. Okay, now we are moving to the third out of three component. Now we have 4 p states, and I'm again not going to comment why 4 p states, because I have no idea. And also we have 3D states, which correspond to titanium atoms, and I also have no idea why. So that's the brilliant zone. There are some points, they correspond to some orbitals. Yeah. Gamma and L symmetry points of normal reciprocal lattice become equivalent gamma points of smaller brilliant zones. So that's the announced idea, which was not explained, that we have shrinking of a brilliant zone, so that points change somehow, and we're told how these points changed. Okay, maybe we can look at. Okay, no, let's look better at this image. So now we have also like exchange of the, I mean, interaction of bands. and somewhere there in the future it will be written that, maybe no, it was written in the discussion of excitonic insulators that here for this material there is an interaction between bands, and here it's written which exactly bands are meant. So bands correspond to some orbitals, and we separate them in different materials. So these are two bands, they interact. And also somehow we have the shrinking of the brilliant zone, and here we are written how the points change from the initial brilliant zone to the diminished brilliant zone. Okay, here we are, as far as I understand, given a discussion of this. Unfortunately, I made a typo. It meant 6C image. So it's not clear what is the gap. Okay, it's meant in the normal phase, so that's what we should look. We should look on this side of this plot, and what is the value of the gap? Maybe that's the minimal value, but also no, I don't know what is meant here. Maybe it's meant from this level to this level, so that's maybe the energy gap. So it's absolutely not clear what is meant. Maybe my interpretation, but I thought actually about this plot when I was preparing to the stream. But right now, during this reading of the article, I think that if it's written in the normal phase, right? Yeah, and that's about the normal phase. So we should look here, and maybe we mean this gap from maybe this band, which is not really resolved well, but still. That's what is meant from this to this. That's approximately 0. Minus 20 milli-electron volts. That makes sense. And this is the 1.5 milli-electron volt for PD interaction. That's my interpretation of what's going on. And this plot should be just approximation from the experimental plot. But there are a lot of things that I don't understand. For example, this band goes here and then it's never. Okay, let's write it here. I mean, most likely the answer to this question is that it goes, but now we have a different direction of the Brilliant zone. So we go on this direction, and we go on different direction, and on different direction there is no this band. But I'm not expert. I wanted anyway to look at it more closer and understand why exactly this band is here, but now it's not here. And before it was somehow a connection between band and continuation of the band. I don't just know how to interpret these plots properly. And here that's written just description of this plot. And we also have these comments, band overlap and band gap. Maybe that means like overlap somehow, but I can't be assured about it. Okay, we will not go today to empirical tight binding model because I'm a little bit tired. I mean, we'll go today, but not in the stream. During this stream, I want already to finish with discussion of this ARPES results. Okay, now there is a strange comment that there should be 3 bands, not 2 bands. But I have no idea why do we need 3 bands, so it's better not to point much attention on it. Some advanced theory should give us 3 bands, and also then some advanced explanation should be, which tells us why don't we have 3 bands. And that's about this sentence. Okay, now we are discussing the right side of the figure 7c, and now we have a semiconductor already, not maybe insulator, but I don't know what we had before. Normal metal, maybe, I don't know. I also forgot what is the statement about semiconductors. It will be maybe below, and it was written which materials can be described as semiconductors. And as far as I remember, it was written that only this tantalum diselenide was a semiconductor. But here it's written that titanium diselenide, I mean tantalum disulfide, was a semiconductor, but here it's in the titanium diselenide, the third material, is also a semiconductor. Okay, let's just believe that both of them are semiconductors, but it's another discussion why they're semiconductors. And okay, let's just write it to my questions. Okay, I have my answer, but I'll double check that I understand it correctly. Yeah, but suddenly we have other ARPES results, and there are some okay, maybe not other results, maybe similar results, so it should be changed here. They're not different because it's written similar shifts are reported. So maybe other results also confirm these results. Okay, now we have also flattening of the top band. So that's the band gap that appears. But also we have the flattening of this band, which we called 4p valence band, but I don't want to comment it. I don't know why we have a 4p band as the top band. And it's written that this flattening is because, I mean, somewhere here, maybe the flattening is because of this interaction, which sounds like a very strange statement. So what is the folded 4p band at L? It's not what I understand. And also we don't actually have, I don't know, it's really strange that we have something here and we don't have anything here. This is the question for these plots, and there is discussion of this flattening, but we don't see them in experiments, so that's why I have this question. Okay, and there is ever unclear reasoning of why this happens. That's the main idea of this sentence. And also buckling of bottom. Yeah, so it's about this bands. Some of this change is called buckling, but everything is very not clear here. Yeah, it's written that splitting is not observed, but we don't see also not observed splitting. So here there is nothing. So we don't see the splitting. We don't see the band at all, and that's why I wrote the question that I wrote just now. Okay, and here we are told that, like, if we see such ARPES results, then we should immediately understand that that's a PD band interaction. Maybe that's this band. Okay, maybe this band, because selenite is the conduction band. Okay, maybe this bands. I'm confused actually. Yeah, maybe that's the selenite for P bands. Yeah, and 3D bands, this is a conduction band. So when we are told PD gap, then it means from conduction D to the valence P bands. And that's why there is this interaction. I mean, that's how we explain this change of the bands. And what is meant by important indirect ingredient for charge density wave. It's better to forget because it looks like it's not connected. It looks like a different framework of description at all, fully different framework. Okay. And it, when it again develop theory for it, unfortunately I used wrong color. It should be a green color. So what is the conclusion about this material? That's the plot. We have a lot of comments, a lot of labels, like names of the bands, ideas of interactions of the bands, ideas why some bands should be there but they're not there. Basically that's all. Nothing is really important. We can just look at this image and that will be enough. Okay, then that's the end of this paragraph. We go to the next paragraph. Okay, here it's written that somewhere above transition temperature, so maybe even at these temperatures, some effects are there that tell us that this will be the case for some lower temperature, and we don't know what is it, lower temperature. I mean, we can't determine it theoretically as far as I understand. It's actually a good idea. Can we calculate TC? I'm not sure. Maybe no. I would vote for no, but I definitely need to read articles and maybe somewhere there is a proposal. Maybe it's still possible, but I don't know how to do it. So here it's written that here at the state above transition temperature, there are signs of of something that will, of the charge density wave for the lower temperatures. It's written like band shadow, diffuse shadow band intensity. Maybe it means this, but I don't know. And I don't know how it is connected to the charge density wave. Suppression, spectral weight. Already occurable. Yeah. And suppression of spectral weight. Yeah. I need to change it. Yeah, I'll change it, just a typo. Yeah, so that's what is stated here. I can't explain you why, but that looks like strange comment. But okay, if you deeply understand what's going on in normal stage, then it might be a like typical thing that you think when you look at the normal state. These are the signs of charge density wave, but I don't have such understanding. And again, we are linking this to the strong coupling nature, additionally to section 3.2, but in section 3.2 there were already some ARPES results, so it's not clear if this is additional experimental results or the same. That's what I wrote here. It's also not clear how is it at all related to the strong coupling nature, because what we're discussing is just interaction of bands, and some theory is assumed which is not explained here. Okay, now we want to explain these results which we see. However, a lot of comments have already been done about it. Now we have unclear explanation. I mean, another question is that where they open. I need to write it also with different color at the points, at these points which we have discussed already. Now, the unclear explanation is that actually strong coupling and two-dimensionality. Two-dimensionality should not blur the image of Fermi-surface. Okay, the blur of image of instability. See, like that's image of instability. That's an unclear statement. That's just a unclear sentence. What is the image of instability and how it can be blurred? It means maybe the I don't know, maybe just blurring of the Fermi-surface at all. Like it's blurred more, and that's the effect. And also his favorite strong coupling maybe has some influence, but I don't know which influence, because it's unclear what he means by the strong coupling, how exactly it should be taken into account. And it's written the charge density gap, and that's what I don't understand. We are told that, okay, what is the charge density wave gap? I thought it's here. Okay, actually it's a good question. Like, and yes, that's the question that it's written. It's not necessarily opens at Fermi energy, but when it opens, that's the question to think about. Maybe this plot can help, but let's see. Okay, for some reason it opens for tantalum diselenide, and by the way, let's just jump ahead. We will not have time for discussion of this today, but tomorrow we will have a discussion of application of type. But today, yeah, okay, most likely tomorrow it will be. So for tantalum diselenide, let's look at some images. No, it's titanium diselenide, and that's tantalum diselenide. So that's the image for tantalum diselenide, and it's written here that Yes. Fermi-surface is completely removed. Fermi-surface pockets. Maybe it's meant that the circles are not circles actually, and density wave gap opens in the Fermi-surface. Maybe I don't know how to explain it. Somewhere here, we should see it. Okay. So I have already stated the question where the gap opens, so I can't comment much now. Here it's written that for some reason it opens in Fermi-surface, but it's hard to see it here from the image. And density wave gaps are not directly connected to Fermi level crossing, but how at all gaps can be related to Fermi level crossing is not the thing that I know. Gap opens between submanifold and somewhat higher binding energies. So we should imagine this image, and maybe it's just a comment about this image. Can I go? Yeah, sorry. How to? I'm just wondering that maybe I broke my app. It's hard to not break it because it's not really developed. Okay, it needs time to load. Okay, I can click here. Now I can zoom out. Now I can open again the PDF. The technology is not so developed for it to work really fast, but maybe later I will develop it better. So we stopped. That's just chapter 3. Pericultate binding model. That's not what we're going to reach today. So here, the sentence that I stopped on brings us to this image. Just need to not to open like this. To this image, and there are different gaps that open. That's written here. And that gaps open between submanifolds. Yes, that's what we see from some time binding model that was announced, because from experiments we don't see. From experiments we see just gaps in the same band, and other effects are rather negligible. That's the explanation that is given, and somehow theory should give us different charge density wave gaps. The question is that maybe I'll understand it later. Here is written gaps, so that's something new for me. Yeah, and that's written titanium diselenite. Okay, I'm showing you tantalum disulfide, but I don't think that we have a plot for titanium. Oh, no, it's fine. Tantalum disulfide. Yeah, not fine. That's for another material. That's for first material. That's for second material. So we just need to believe that that's the plot for that somewhere there's plot for tantalum disulfide, and we see something similar, like it's no, that's fine. Here that's the proper plot, so these are the gaps, and we have just the description of it, and these are the gaps that we see, and that's here. And I want to remind that I don't understand what is this gray area that don't correspond to a black line. I can't answer you this question. I need to read some original paper to understand it. Here it's not explained. And okay, we are left with 2 last paragraphs before the end of the stream. Again, we are asked the same question, how charge density wave is connected to the band dispersions. We were not given any answer, but there were some statements which were unclear. Again, the statement about these bands with higher spectral weight and gray areas. What about exceptions? Let's check. I wrote some question which I don't remember. Okay, that's my lack of understanding here. It's not a real question. It's meant that we're not able to detect bands. We can detect only these areas of the bands. It's also not clear why do we have this gray area here. Let's write the question here. Okay. That's not clear because I was thinking about this gray area, and this gray area is not really looking like something here. That's the question. Gray area. So I will try to answer it later. It's very strange that there was a gray area there and no like distinct band which will correspond to gray area here. Okay. Okay, that's there. This is the statement. And that's surprising, and it's confirmed. That's the sentence doesn't give us something useful and meaningful. Okay, now we are given a statement about the fine structure. So you see that this is not a consistent text. Here it's written about this consistency of charge density wave and band dispersions. So how it is reflected. So how it is consistent, it means, or like, yeah, if we see different band dispersion, what can we say about the charge density wave and vice versa? And we are written that, oh, actually, there are different spectral weights, and that's surprising, that's confirmed, and what's written here, it's not really clear. And here it's written about some fine structure. And some bands can be identified, some cannot be identified. So we're given just some abstract comments which are not related to the question that was in the beginning of the paragraph. So nothing is useful here. That's the conclusion. Fortunately, this article has some text which has very little meaning and very little value. Okay, now there is introduction to tight binding model. So that's what we want to do. We want to understand these band structures. Oh, by the way, why do we work? Okay, that's the question from our general education, because we have different limits of electronic models in the lattice, and we are told that the tight binding model is applicable, meaning that we have a close to insulator state. But the question is that why is it so? What is the reason why we start with this model? I mean, we can say let's try and check, but I don't know. Maybe we can say that, oh, in tight binding models we have a cosine by default, and here we have something that looks like cosine, so we can fit it into many cosines. And maybe that also works, but I wrote the question for my later understanding. It's just about this motivation of the tight binding model. Provide access to complete reconstruction. Okay, here it's written that if we can predict spectral weights, then maybe we can predict also band structure and also some other bands, not just the part of a band. But that's like a bad motivation. Like tight binding models should explain all of this, right? And we, as far as I understand later, we'll see. Actually, I have this plot, so we will see that yes, they do simulate it fine in a fine way. So that will be the topic of next stream after I have a rest. I thought to do it in this stream, but I see that it's impossible. That's too much for me for one stream because I'm not expert in this topic. It takes too much energy right now. But that's the announcement of here, of what we will see here, that for the let me a little bit scroll. For the original band, we have this fitting and then this reconstruction if we go to chart density wave. So it sounds like a really great model. That's what should we think about if we read this sentence. And possible mechanism. Yeah, that's the useless statement. I should erase this, just useless statement equal to this statement. Then again, we can hope that we can get some insights about chart density wave mechanism as we do throughout all of this article. Maybe now tight binding models will give us some insights. Spoiler, most likely no, it will just be a great fitting, and you can maybe work with just tight binding models and be happy. But some general questions of the formulas will be unanswered, but with such approach from this paper, of course, they will be always unanswered. It's very unstructured theory, not consistent theory, a lot of too detailed comments, which are really not needed. But okay, let's just review shortly what we have done today during this stream after this thing will finish. Yeah. So review of ARPES results. We did 1 page, 2 pages, 3 pages, 4 pages, 5 pages, 6 pages, 7 pages approximately. A little bit less, but that's fine. 7 pages per one stream. So we have discussed in general, I don't even remember what happened here, general features of ARPES results. These are different plots for 3 different materials. Then we discussed each of them, like tungsten disulfide, some comments about what happens on that plot. Again, tungsten disulfide something. Then we have this unclear statement of what happens here. Maybe that's only from experimental plots, but here it's written taken from experimental theoretical plots, so it's not clear from what is taken exactly from theory. But we have discussed what is the change of the Fermi-surface in the Brillouin zone and the Brillouin zone itself, by the way, somehow. But I don't understand this statement about. Actually, it's a really good question, which I should point out. That's what I don't understand, of course. That's the well-known statement throughout this article, but I need to really think better about basics of condensed matter to understand it. But that's how it happens, that Fermi-surface changes, Brillouin zone changes, bands change, spectral weight becomes only in some parts of these bands. And we have basically three types of ARPES measurements, but the last type is very similar to the first type, it's just different direction for some reason. But okay, then we have a discussion of all other rest two materials, tantalum diselenite and titanium diselenite. And that's just basically advanced description of what we already see on these experimental plots. That's all what we did, and then some useless comments and some useless connections, very unclear connections with the, for example, mean field model. Yeah, I even forgot, did we discuss it? Yeah, I think we did discuss. So maybe if we go to the path of mean field model, which we had discussed before, then we need to do the strong coupling and some clever extension to 2 dimensions, but maybe it was written that these are interconnected, so it would work with 2 dimensions, then we already have some features of strong coupling. And then we have a discussion of the gaps. We see, like, the author writes a question, then he gives not related comments, and again, question, not related comments, then motivation for the next section. So I was spending my time just to show you that not so much value is there in these parts of these articles. And okay, so it's time to have a break. I was thinking about topic that I'm not expert in, and I see that my app really helps. I don't know what can help me better, maybe AI chat, but AI chat can make just a mess of information, so I prefer to do this framework that I think on my own, then I present what I understand, then I have a little final discussion with the chat, maybe if I want, but the thing is that not always we want to have some advanced understanding. Sometimes we are fine with understanding just statements and not trying to figure out why it's like it's stated. That's the case for this article, for all other articles that have been discussed in these streams. So maybe later, I mean, definitely later, I will try once to discuss these questions with the chat. Maybe we'll get insights, but it's easier to just try to understand on your own and only if needed go to AI helper. But again, it's about the comfort. So if I had my application working, I would have chat and I would speak more with the chat. So thank you for your future attention. And today later, I will finally try to work out tight binding models. During this stream, that's already enough. We have learned just summary of experimental results of ARPES measurements for 3 materials here. Maybe it will be useful. I don't know. Rossnagel thinks that it's useful, and all 1,000 people who cited his paper also will not be against the statement that it's useful. So see you maybe in some hours or half a day. Bye-bye.